Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of a video on quadratic functions, kind of a review video for those who are in college algebra. And in this video, we're really going to focus honestly on applications. Applications of quadratics, maximizing or minimizing values. Even though it's titled Determining the Maximum and Minimum Values of Quadratic Functions, I am approaching this from an application perspective. So let's recall the output of a quadratic function at the vertex is either a maximum or a minimum value for the function, depending on the orientation of the parabola. The idea of maximizing or minimizing a function is often called optimizing, and it's essential in mathematics and business applications. So how do you do that? Well, there's a couple ways you could do this. I do it via graphing to find the vertex, but a lot of people will do it using this formula we talked about last time. So it just depends on your choice of how you do this, but I really like to reinforce a natural understanding of the quadratic function and how it's graphed, and how its graph is very natural to understand. So let's go ahead and take an example here. Find the dimensions of the rectangular corral producing the largest enclosed area, which is split into 3 pens of the same size, given 500 feet of fencing. Now that's a lot to digest. So let's see, we want to find the dimensions of something. Okay, so that's like a width and a length. So I'm just gonna point an arrow at that and make it known to myself that I want length and width of this rectangular corral. Generally, my tactic when I read some type of application problem, or if I'm dealing with real world mathematics, is I simplify it down as much as possible. So let's see, what else do we need? Find the dimensions of rectangular corral producing the largest enclosed area. Okay, so I need the formula for an area, right? If I said largest enclosed volume or perimeter or surface area, I would hunt for formulas involving volume, surface area, or perimeter. In this case, they specifically say they want the largest area. And as long as we know it's a rectangular corral, which they told us it is, then I know area is just length times width. So let me write that down as well. I'll zoom in on that. So I'll point an arrow at that and I'll just say it's length times width. And we're going to split that into 3 pens of the same size, and we are handed 500 feet of fencing. Okay, now I'm going to draw a picture. So I haven't talked about it in this course, but there is a method of solving word problems and applications, and it's called Poya's problem solving process. Let me write that down. And the very first thing you're going to do in this problem solving process is you're going to read the problem. You always want to have a win, right? So the very first thing you need to do is read the problem. And obviously, if you don't read it, you go nowhere, right? The second thing you need to do is try to understand what you've read. And this means that you're going to reword things, maybe, or draw a picture. Those are kind of my go-to methods there. And actually, you saw that I was sort of rewording things. I actually started inserting mathematics here, want L and W, and then I knew that area is L times W. So really, I'm starting to kind of build the mathematics in, but for most people, they just start rewording it. They state it in a different way so that they can understand it. And drawing a picture, actually, that's what I'm going to do right now, because this deserves a picture. You can see that that is a rectangular corral. A corral is just an area, rectangular area. and there's a fence line all around it. And we're going to break that into 3 pens of equal size. So I'm going to have a little sub pen right here and a little sub pen right there. And hopefully, roughly, those are the same size. So that is a visual of what's going on. So I've drawn a picture. And the next thing you're going to do in Poya's problem solving process is you're going to list things that you know that you've been kind of handed in the problem. And you're also going to label things that you don't know. So for example, here, one thing that I definitely know is that we have 500 feet of fencing. So I'm just going to write that down, 500 feet of fencing. That is something that's been handed to me. Something else that I know, well, I have 3 pens of equal size. Drawing the picture kind of showcases that. Okay. But the things that I don't know what the overall length is. So I'm going to go ahead and label this distance here, the length. And then let me go ahead and write that word in there. And I'm going to label this distance, the width. Let me do that really quickly. So this is W, which I'm going to call the width. Notice that I haven't involved any formulas yet. I've just kind of slowly built in what I'm given here. And while I'm doing this, I'm going to go ahead and make little notes. Like, for example, this distance right here is a width. So is this, and so is this. In fact, I'll just call all these little pieces widths. And if you really want to talk about like the pieces of this, I suppose I could say that this is 1/3 the length, this is 1/3 the length, and this is 1/3 the length. And so is this actually, right? So I'm really overstating all the stuff they've handed me, but sometimes I feel as though it's a little safer to list out as much as you can, because then it might really help you in the end. Now, the next thing we need to do is really kind of start including mathematics. We already kind of have here, right? We've started labeling things, but it's really important now to really glue the math to what we need to know. So I think it might be nice to list out an extra step here. We're going to create an equation, or maybe several equations, using the unknowns that we kind of pulled together from our previous step and the thing you're being asked to find. The thing we're being asked to find here is find the dimensions. Okay, so we're asked to find the dimensions, which are the things that we labeled, right? L and W. But it's very difficult to actually create an equation with just L and W. Those are expressions. So we have to find something else in this language that relates length and width. Well, we have a couple things actually. One that is already highlighted and stated. Length and width, that's equal to area. Length times width, I should say. So I'm going to go ahead and in this step, just write down in black ink right down below, I'll just say, well, I know that length times width should be the area. The problem here is that we have way too many variables. You would like to have only 2, because what you want to do is graph this. And there are 3 unknowns here: the area, the length, and the width. Because there are 3 unknowns, we will need another equation to relate 2 of those unknowns. And luckily, we do have within this problem another statement. We haven't even highlighted it, but I will here. So I know we have 500 total feet of fencing. That means 500 should be the total amount of fencing that we use here. All of this highlighted stuff right here is all fencing. The sum of all that highlighted length should be 500. That is L, this full length right here, plus another L, the full length down there, plus 1, 2, 3, 4 of those widths. 2 of the L's plus 4 of the widths. That should be 500. This is what you want. You want to be able to relate out one of your variables. It doesn't actually matter which, but notice I have 1, I'm going to point arrows here. I have 1, 2, 3 unknowns total. right? Because L is repeated here and W is repeated there. So I have 3 unknowns total. I have 2 equations. That means that 2 of your unknowns can be related to each other. And so really, you'll just have 2 unknowns. I'll show you what I mean. So let's see, what else do we need to do? Create an equation. Oh, and then solve that equation. So 5, solve, 6, check for reality. And then finally state your solution. Now this is a very oversimplified version of Polya's problem solving process, but it gets the job done. So we have 2 pieces of information. We want to maximize the area. And in fact, if you're dealing with optimization problems, which you will in calculus, the step right here in step 4, really the equation you're going to create here, one of them at the very least, is the equation which is about the variable that's being optimized. So create an equation for the variable being optimized. And that kind of helps out significantly because what we want to optimize is we want to optimize the area. We want the largest area. That means the maximal area. So I want to keep the area formula, but I need to somehow glue length and width together. Luckily, I can solve that bottom equation for either length or width. I'm actually going to solve for length. So this bottom equation, I'll write my solution in blue here. I can get 2L is equal to 500 minus 4W. Or in other words, wherever I see an L, it's going to be 250 minus 2W. And luckily, I see an L right there. So that's what I mean by that you really only have that A equals LW is actually only an equation in 2 variables because we're going to sub out the length for 250 minus 2W. Let me write that down. Thus, we want to maximize the area, find the largest area, but area is length times W, length times width, sorry. But we just found out the length can be written as 250 minus 2W, and the width is just width. Now, if you look at that equation, so that implies we have area is equal to, again, 250 minus 2W times W. If you look at that, this is super duper easy to graph. I can optimize this. A lot of students or a lot of instructors might say, oh yeah, multiply through and use negative b over 2a to find the vertex. I'm not going to do that because that's not the way my brain works. Here is the W axis and here is the area axis because this is a function, A is a function of width. And what I'm going to do here is just ask, well, when does this function hit the vertical axis? When does it hit this vertical axis here, right? And so that happens when we let W equal 0. That's when we hit the vertical axis. And if you let W equal 0, that will imply the area is 0. So one point that exists on the curve of this quadratic function is 0. And then my second question is, well, when is the output 0 again? I'll write that down. When is the area equal to 0 again? Well, it's very nice because somebody, we did, already factored this. So if I let area be 0, that will imply that we're working with 0 is equal to 250 minus 2W times W. Well, that happens when obviously W is equal to 0, but also when W is equal to, if you set this piece here equal to 0, you get W is equal to 125, right? Set it equals 0, you would then move 2W over and divide by 2, and so you would have 250 over 2, which is 125. So now I know the area is 0 at when the width is 0 and when the width is 125. Somewhere way over here. Here's 125. Halfway between is where the vertex will be. Because remember, this is a quadratic function. Had you multiplied through, which I'm not asking you to do that, but had you multiplied through, you would have gotten negative 2w squared plus 250w. That is an upside down parabola. So I am just going to say, well, our vertex, I know it's upside down here, our graph, and I know the vertex is halfway between these 2 points. Well, halfway between 0 and 125, that's where our vertex is. Let me go ahead and write that down at 62.5, mainly because it's halfway between 0 and 125. So I'm going to go ahead and mark that here. This x value, or w value really, is w equals 62.5. So I know that my area, remember this is the area function right here. So my area reaches a maximum when my width is 62.5. Remember what we're talking about, these corrals right here, right? And so we know that the area becomes maximum, and that's what they're asking for. Find the dimensions when we have the largest enclosed area. And we know we have the largest enclosed area when width is 62.5. Now our only thing we need to find from there is what's the length. Luckily, I have a formula relating length and width right here. Actually, I could technically use this guy right here. So I'm going to use this formula right here to help me find what the length is for that corresponding width. I'll zoom out and I'll just mention it down here. Since the length is equal to, I forgot what it was equal to, so I'm just going to look back. 250 minus 2w. The dimensions, which maximize the area, are width is equal to 62.5, and length is equal to 250 minus twice 62.5. Twice 62.5 is 125. 250 minus that is 125. So that seems pretty darn realistic. You could go back through and double check to make sure that the sum of, let's see, 2 of those lengths and 4 of those widths would be 500. It will be. And it will present a maximum area. They didn't actually ask us what that maximum area is, but we could totally find it because you know your area function is right here. So you could totally plug in, if you wanted to, if you were asked to, you could plug in 62.5 into those W's because that's where you get the maximum. And I'm just going to do it because I want to. So that'd be 250 minus twice 62.5, which is 250 minus 125, which is 125 times 62.5. So the maximum area, I'll write it down over here, 7,812.5. And I think we're in feet. I'm just going to assume we are, but I'll have to go and check. Nobody asked for that max area, by the way. Yeah, feet. We have 500 feet of fencing, so we're in the units of feet. That's how I maximize or optimize using quadratics. I really just graph it out using symmetry. I know when it hits the x-axis, or when it hits the y-axis, when it will be at that height. Again, halfway in between will be the maximum or the minimum. So let's try another problem, because one is not good enough with an application. So here's the very last one. And this, I love these styles of problems. These I give to my Algebra 2 students. And you should probably, because you've gone past Algebra 2, you should be fine with this stuff. But these are great for business models. So when a business charges $600 for a seminar on management techniques, it attracts 1,000 people. For each decrease of $20 in the charge for admission, an additional 100 people will attend. That makes sense. You lower the price, more people show up. If we let X represent the number of $20 decreases in charge, then we can find the revenue function and then find out when we have maximum revenue. That's the whole idea. If you own a business, you want to know what's the optimal price I should charge. Same thing, like you could do this for rents, for apartment rents and stuff like that. It's very sad to find out that you optimize revenue when you leave apartments unrented. That's very, very sad because you want to help people out. But business strategy wise, it makes no sense to have all your apartments rented. And this is kind of the same thing here. So let's see. They charge $600. So let's write down a few things here. First thing I'm going to notice, I've read the problem. I know what's up. Right? Second thing I'm going to do is try to understand what's going on. And if you don't understand what's going on, well, that means that you need to either draw a picture or reword it. To me, this makes sense. Normally charges $600, you get 1,000 people. If you drop the price, more people show up. Great. So the third thing I need to do is start labeling stuff, right? Start listing out things that I want to know. Start listing out things that I don't know. And one thing they were kind enough to hand me is the fact that we're going to let X be the number of $20 price drops. So if X were 1, we're dropping the price by 1 set of $20. If the X was 5, then we're dropping the price by 5 sets of $20. That should make sense. And the other thing that we need here is we want to mention what we want to optimize. And that comes in part B, but I'm just going to write it anyway. Find a value that maximizes the revenue. So I'm going to list that over here. I'll just say maximize revenue. When I say maximize at this point in mathematics, I think, okay, this must be parabolic. Now, this requires you to know a little bit about revenue. Revenue, a very important formula, is how much you charge, which we call the cost, times the number of items sold. Number sold. That's what revenue is. So if you sold cars and you sell them for $10,000 each and you sell 10 of them, you've made 10 times 10,000 or $100,000. So that's what revenue is. It's not profit, it's revenue. Okay. So let's go ahead and now start introducing mathematics. That's kind of what step 4 is. Introduce the mathematics once you label things. So the mathematics here. Well, revenue. Let's go ahead and actually initially state what revenue is. So revenue initially is, well, we charge $600. So I'm going to say revenue normally, we would charge $600. I'm going to leave some space there. And the number of tickets that we normally sell, well, that's 1,000. So I'll go ahead and say we normally sell 1,000 tickets. That's actually quite a bit, right? 600 times 1,000, that's 600,000, right? So that's really good. I'm pretty happy with that. But what if we can make more money? Well, let's see. What I'm going to do is adjust this based upon the number of price decreases. So X is the number of price drops. So let's see. What is the new ticket price if we increase it just by one set of $20? So X, I'll make a little table here so you can see what I'm talking about. If X were 1, the new cost for somebody to attend would be the 600 plus the extra 20, so 620. And I'm going to say that's the same thing as 600 plus 20, right? That's really what it costs. It costs them 600 plus $20. If I did 2, these are price drops. I'm so sorry. These are price drops. So it's not 620, it's 580 because that's 600 minus a price drop of $20. I apologize. If I did 2 price drops, well, it would be $560 as a ticket price, and that's because it was originally 600, but you're dropping it by 2 sets of $20. If I did 3 price drops, you should see the pattern now, but if I did 3 price drops, well, it would be $540, again, because you initially charged 600, now you're doing 3 drops of 20 off of that. In general, the cost you can see is 600 minus whatever the number is times 20. So in general, if I had X price drops, then the price to get in would be 600 minus 20 times X, where X is the number of price drops and 20 is how much it drops each time. Now let's talk about the number of people who are attending, or number sold is what I would say. Number sold. Well, initially we have 1,000 people showing up, right? But we drop the price. And every time we drop the price by $20, we get an additional 100 people. So let's see, if I drop the price by $20, we will have the initial 1,000 we have always had, plus 100 extra people. If I drop the price twice, I will have the initial 1,000 plus 2 sets of 100 extra people showing up, and so on and so forth down the line. You can kind of see the pattern. So in general, if I did X price drops, I would have 1,000 plus 100 X people show up. Now, this is a quadratic. Had you multiplied this out, this would be a quadratic function, because you'd have, I don't think you should do it, but I'm just going to showcase this. You would have a negative 20x squared plus ... right? It is quadratic, but you should not multiply that out. You also should not do what I did in the last problem, which is to say, oh, you know what? Let's find out when this function hits the vertical axis, because that would mean I'd have to multiply this out, and I don't want to. I suppose I could, but I don't want to. Instead, I could ask, when does it hit a different axis? Specifically, when does this function hit the x-axis? And the reason why I'm asking that question is because if I know when a parabola hits the x-axis, and I know that this parabola goes upside down because it's a negative 20, actually not 20x squared. I wrote that, but it should be negative 2000x squared. Anyway, the reality is that it's an upside down parabola. So if I know where it strikes the x-axis, and I know it's upside down, then I know this function has a maximum halfway between where it strikes the x-axis. So this is actually very nice. The rule of thumb is if your function is pre-factored like this, just find the x-intercepts. That's a great rule of thumb. So let's see, when does it hit the x-axis? Well, it hits the x-axis when 0 is equal to, in other words, the output, the revenue, is equal to 600 minus 20x times 1,000. That's supposed to be a 1, but my pen went wacky. Plus 100x. Let me clean up that 1. All right. And solving this is actually fairly simple because it's already pre-factored. Either 600 minus 20x is equal to 0, or 1,000 plus 100x is equal to 0. That is, either x is equal to, to move the 20 over and divide by 20, x is equal to 30, or move the 100x over and divide by a negative 100, x is equal to a negative 10. So let's see. I know that it hits the x-axis at negative 10 or positive 30. Halfway between is going to be the vertex. Halfway between is where we maximize our revenue. Halfway between is where the vertex is. And remember, the vertex is a maximum in this case because, again, that parabola is opening downward because the lead coefficient is negative. Negative 2,000, not negative 20, but whatever. Anyhow, so halfway between negative 10 and 30. How do you find halfway between two numbers? Well, I don't know. Let's suppose that I give you 8 and 10. What's halfway between? You would say 9. Mathematically, you would say 8 plus 10 is 18. Divide by 2. You're averaging. You average numbers to find what's halfway between them. So halfway between x sub half, I'll call it, you would just add up the numbers and divide by 2. You're averaging them. That'd be 20 over 2 or 10. So I'm going to go back over here. So I found out, yay, we maximize revenue. Revenue is maxed when x equals 10. But what does that mean? It means we need 10 price drops. Implies 10 price drops. And remember, each price drop is $20. So implies drop price by 10 times 20, which is $200. So instead of charging $600 per person, now each person should pay $600 minus $200, or in other words, $400. And you say, that gets me more money? Yeah, absolutely, it does. The reason why is if you go back to the very top here, right here, if you didn't have price drops, you made $600,000. That seems like a lot, right? However, with the price drops, if you allow X to equal 10 in those, in the revenue equation, R of 10 is equal to 400 times, let's see, 10, right? So 1,000 plus 1,000, right? So 2,000. That's $800,000. Compared to your $600,000. You're making more money, even though you're charging less. It's because you have more people showing up. Now, I didn't even bother looking at the questions. I should have, but the first one says determine a revenue equation, which we did. It's right here. Second part says find a value of X that maximizes the revenue. We did. That's X equals 10. But I went a little bit further and I just said, well, 10 price drops. So we dropped the price by $200. So the new price should be $400, which means we'll make $800,000. This style of problem, really powerful, very powerful. If you have a business, I highly recommend that you just give this a whirl. If you sell widgets for $80 each and you just don't have a lot of customers, start dropping the price and let it sit for a while and see how many customers actually buy. Now, of course, there are so many things that drive a market. So it's not just price, but demand. You could have a very cheap product, but nobody wants it. So, oh well, that's just how it is. But if you sell quality products and people want them, then you have the ability to play with price and maximize your revenue. All right, so that's it for determining maximum and minimum values of quadratic functions. And that also rounds out the topic of quadratic functions. So I hope that was okay.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.